So, what if I told you your brain cracked one of the biggest puzzles in artificial intelligence, like way before we even knew it was a puzzle? Today, we're diving into this really mind-bending connection between the front part of your brain, your prefrontal cortex, and the AI dream of learning how to learn. All right, let's kick things off with a little paradox. Think about the last time you picked up a brand new video game. You probably started getting the hang of it pretty quickly, right? You were adapting in minutes. But here's the thing. We know that the physical changes in your brain, the stuff like building new connections, that process can take hours or even days. So how is that possible? How can we learn at the speed of thought when our brains are changing at the speed of biology? Well, it turns out the answer is that we're basically running two different learning programs at the same time, each on its own clock. You've got the fast, right here, right now adaptation, and then you have the slow, deep skill building that happens over your whole life. Let me put it this way. Fast learning is like figuring out your buddy's favorite cheat move in a fighting game in just one match. Slow learning? That's the thousands of matches it takes to become a grandmaster. See the difference? One happens inside a task, the other happens across countless tasks. So what's the bridge here? What connects this lightning-fast learning with the slow and steady rewiring of our brains? Well, to find a really good theory, neuroscientists look to a place you might not expect, the world of artificial intelligence. Yeah, in AI, there's this really cool concept called meta-reinforcement learning, or meta-RL. And the goal here isn't just to teach an AI to do one thing perfectly. No, the idea is you throw thousands of different but related tasks at it, so it's forced to stop just memorizing answers and start actually building its own fast learning algorithm that it can use on problems it's never seen before. Meta-RL pulls this off with a really clever two-part system. First, there's a slow outer loop. You can think of this like a really patient teacher. Over tons and tons of trials, it slowly tweaks the AI's network connections to build a really solid learning strategy. Then you've got the fast inner loop. Now, this loop doesn't change any connections at all. It's just the real-time flicker of signals that uses the strategy the slow loop built, letting it adapt instantly to whatever's happening right now. And that is the absolute key. The AI isn't just learning a solution to a problem, it's building a general-purpose learning engine. Through all that slow training, it figures out how to explore, when to just use what it knows, and how to update its plan on the fly. And it can use that skill instantly on brand new stuff. And this is where things get really wild. A bunch of neuroscientists looked at this and asked a pretty radical question. What if this isn't just some clever AI trick? What if this is literally a blueprint for how our own brains work? What if we have a meta-RL system running inside our heads? Okay, so if the brain does have a system like this, where would it be? Well, the prime suspect is the prefrontal cortex, the PFC. And honestly, the evidence is pretty convincing. First off, its structure is what's called a recurrent neural network, meaning signals can loop around, which is perfect for holding on to information for a short time. It's also constantly getting updates about what we just did and whether it worked out. And here's the kicker. Its connections are slowly shaped by dopamine, our reward chemical, but its moment-to-moment activity is super fast. It's got the perfect setup for both that slow teacher and that fast learner. The researchers who proposed this put it perfectly. They said to think of dopamine as that slow outer loop, gradually carving out the wiring of the PFC based on a lifetime of trial and error. But once that network is trained up, its own internal chatter, the firing of its neurons, can act as a fast inner loop, updating our strategy in the blink of an eye without having to wait for the brain to physically rewire itself. So here it is, the main idea. Your prefrontal cortex is a meta-learner. Over your entire life, it has been slowly trained by experience to become this incredibly flexible learning machine. That feeling you get when you're getting the hang of something, that's not your brain rewiring itself in real time. It's a pre-trained algorithm kicking into gear. Okay, that is a really cool theory. But how on earth could you test it? Well, researchers did something pretty clever. They built a computer model of the PFC based on these meta-RL rules. And then they gave it a classic cognitive test, the ability to slam on the brakes on an action you've already decided to take. The test is called the stop signal task. It's super simple, but it tells you a lot. Most of the time, you just see a go signal, and you have to do something, like press a button real quick to get a reward. But every once in a while, right after the go signal, a stop signal flashes, and you have to try and cancel the action you just started. It's basically a race between your brain's go command and its stop command. So real quick, in the brain, dopamine works through a couple of main pathways. You can kind of think of the D1 pathway as the go signal, and the D2 pathway as the whoa, hold up, or break signal. So the researchers tweaked these in their model, and what they found was really surprising. Just look at that top row, stop time. When they weakened the go pathway, the D1 pathway, the time it took to stop an action shot way up. The brakes got way slower. But messing with the break pathway, it didn't really do much to the stopping time. It wasn't a simple tug of war. One of these pathways was clearly calling the shots.
And this led their model to make a really specific and kind of weird prediction that D1 go pathway isn't just for starting things. It's also the main thing that controls how fast you can hit the brakes and stop. So it's not a simple gas and brake system. Paradoxically, the gas pedal seems to be what also controls the brakes.
So how does this go pathway manage to be so good at stopping? To figure that out, the researchers looked at something called entropy. Now don't worry, in this context, just think of entropy as a measure of your brain's uncertainty about a decision. High entropy means your brain is still weighing its options. Low entropy means it's locked in, it's made a choice. And when they measured the model's entropy, whoa, the difference was huge. As you can see on the chart, on the normal go trials, entropy was pretty high. There's that little moment of uncertainty before you act. But look at the successful stops. On those trials, the entropy just collapses. There's a sudden massive drop in uncertainty as the system goes all in on the stop command. So being good at stopping isn't about being hesitant. It's about making a super fast total commitment not to act. You know, the really cool thing about a model like this isn't just that it can explain things we already see. The real power is that it acts like a treasure map, pointing scientists toward new discoveries by making these really specific predictions about how the real brain ought to work. And this model produced some absolute gems. First, it predicts that the D1 receptors in your prefrontal cortex are the main knob you'd want to turn to change how fast someone can cancel an action. Second, that the way brain chemicals like serotonin and dopamine work together isn't fixed. It actually changes depending on what you're trying to do. And third, that we should be able to literally see this collapse of entropy and the electrical signals of real neurons in a real brain. And just like that, you've got concrete questions for neuroscientists to go test in the lab. This really changes the game for both neuroscience and AI. For neuroscientists, it helps us move away from a simple, this chemical does that one thing view, to a much richer, more dynamic picture of how the whole system works together. And for AI, it gives us a powerful, brain-inspired blueprint for building truly adaptable agents. Not just AIs that learn, but AIs that can change how they learn as the world around them changes. So this whole framework suggests that our incredible flexibility and intelligence comes from a lifetime of slow training that has built a fast, powerful learning algorithm right into our prefrontal cortex. It solves that paradox of how we learn so fast. And it leaves us with one last pretty cool thought to chew on. If our brains are fundamentally built to learn how to learn, what are the limits? What else can we teach them to do?